Okay, so in this video we're going to be looking in a bit more detail about esters. Now we did previously discuss them. We looked at some of the ways that you can make an ester in not too much detail, and we looked at the main sort of reactions that produce an ester. So what we're going to do today is look at it in a bit more detail and look at some of the properties of esters. So first of all, we've got our questions. So you know the deal with this. Hopefully we'll be able to do those all by the end. Okay, so first things first, if you could just draw the general structure of an ester. So hopefully this is quite easy to remember because we looked at it before. So what's the general structure of an ester? You could draw that down and we will go through it. Right, nice and easy. So we've got the two R groups. They could be the same, they could be different. But the important part is this carbonyl and this ether link here. So we've got a carbon bonded to an oxygen, which is then bonded to a carbon, and whatever else group we'd have here. And forming an ester is all about forming this bond right here. Yeah, so forming this bond between this carbon and this oxygen, that's our esterification reaction really, and that's our ether link there that we're forming. So making an ester from an alcohol, which we did look at in not too much detail. But we do know that we get a carboxylic acid with an alcohol under reflux, acid catalyst, such as sulfuric acid, which is denoted here as H+, and will form an ester and water. Okay, so it's an esterification reaction, also a condensation reaction because we're forming a small particle, small molecule, and this is reversible. Okay, so if we form this ester, it will then hydrolyze, so this water will then react and it will hydrolyze and it will go back and form the carboxylic acid and the alcohol. And if you left it under reflux, you'd get this equilibrium position, equilibrium setup, whereby you'd have dynamic equilibrium. So we'd have the carboxylic acid and alcohol constantly reacting to form an ester, which would then constantly be reacting with some water to form the alcohol and carboxylic acid again. So it is reversible. We'll never get 100% of this ester from reacting these two together. So the question then is, how can we manipulate this reaction to get more of the ester? If we want to get a high yield of ester, what could we do to this reaction? So if we have a fixed volume and concentration of carboxylic acid, what could we do to shift the position of equilibrium to give us the highest yield of ester possible? So the forward reaction obviously is esterification, and the reverse reaction is the ester hydrolysis. So we want to increase the yield of the ester by basically encouraging the reaction to go in this forward direction, to basically do the esterification reaction at a faster rate than the ester hydrolysis reaction. So give you a second to think about that. So pause it here, give it a go, and then we'll go through the answer. Okay, now basically what we want to do, because we can't change anything with the carboxylic acid since we've got the fixed volume and concentration. We don't have any information about the delta H of this, so we don't know if it's exothermic or endothermic, and it's not involving gases here, so pressure is not very important. So what is important is our reagents and our products. Now if we want it to go into this forward direction, we want to flood basically the reagents with alcohol. So we want excess alcohol, we want to use as much alcohol as possible, and that will force this reaction to go in this forward direction. And at the same time, we want to remove this water, because if we remove this water, not only will there'll be much less water available to hydrolyze the ester, but it will also force the reaction again in this forward direction. So we want to perform this esterification reaction, we want lots and lots of alcohol, and we want to remove water when possible. So that's the way we want to do that. Now, we've also looked at making an ester from a phenol, and we've said that the OH in the phenol is much less reactive. So we need more vigorous reagents, okay? And what we use is acyl chlorides. So these are basically derivatives of carboxylic acids. So you've got, obviously this carbonyl here, and instead of the OH, we have this chlorine. So we've got this acyl chloride, which can react with our phenol to form this ester here. This reaction will occur at room temperature, but again, we must have no water there. Okay, so for this reaction, it must be done in a complete absence of water, because obviously any water that is there will react with this ester to hydrolyze it and form our it will form our phenol again, and then the carboxylic acid. So we don't want it to go. We don't want any water there to be present. You can also use anhydrides. Okay, so you can use ethanoic anhydride, which is this, instead of acyl chloride, and it's often used instead of it because it's less dangerous to use. It's not toxic, and it's safer to use. So we can use these anhydrides, this ethanoic anhydride, instead of acyl chloride when we want to form an ester from a phenol. Okay, so we're just going to discuss naming then. The esters are actually named in two parts. So the first part of the name comes from the alcohol that was used, and the second part comes from the acid or the acyl chloride, or even the ethanoic anhydride. So that the acid part. So for this one here, we would have methyl, which came from the methanol. So this bit is the methyl, and then this part is the ethanoate, which came from the ethanoic acid. So we'd call this methyl ethanoate. Okay, so the bit that comes from the alcohol always comes first, and then the section that came from the ethanoic acid, from the carboxylic acid or the acyl chloride or whatever. Okay, and again, it's the same way of naming. You can just count the carbons to know, what you would call that. And yeah, so it's always two parts. First part from the alcohol, second part from the acid. So what I'd like you to do is have a go at practicing these four. So we have 4 different esters there that were all made up from an alcohol and a carboxylic acid. So they were all made using an alcohol and a carboxylic acid. And what I'd like you to do is name them all. Okay, so pause it here, draw them down first, and see if you can name them. Right, so first one, ethyl propanoate. Ethyl, because obviously this is the 2 carbon part, this came from the alcohol, and the propanoate because it's 1, 2, 3 carbons, and that's obviously from propanoic acid. So ethyl propanoate. Over here we have propyl methanoate. Okay, so we've got propyl because this section came from the alcohol, and it's 3 carbons long, and then this part which came from the carboxylic acid, and it's just 1 carbon, so that's methanoate. Then we have methyl butanoate, so the methyl bit obviously from the alcohol, 1, 2, 3, 4 carbons long, so butanoate from butanoic acid. And then finally propyl ethanoate, so 1, 2, 3 carbons long, came from propanol, and 2 carbons from this carboxylic acid, so that's ethanoate, so propyl ethanoate. Hopefully those are clear. You may need some more practice with those. Write down if any of these that you didn't really understand fully, and you can check with a teacher in class, and hopefully you'll be able to practice a few more of these in the lesson as well. So here we have a phenol reacting with our acyl chloride, and when naming here we use phenyl as the beginning group, because obviously it's not an alcohol we're using, it's a phenol. So we just, in the same way, we just add a YL, so phenyl, and then the other bit would be exactly the same. Okay, so in this case, if this was CH3, that would be phenyl ethanoate. Yeah, so yeah, phenyl ethanoate. Okay, so we just need to discuss a few of the uses then of esters. Now, they have very, very characteristic sweet smells. Most of them are quite fruity. And because of that, they're used in food flavorings, perfumes, fragrances, things like that. And a lot of the fragrances are actually things that we're very familiar with, very characteristic. So obviously we've got some here, raspberries, pears, apples, jasmine. All those smells are actually from these esters. So these esters are responsible for these different characteristic smells. And if you make these esters, you will actually sort of replicate those smells. So what I'd like you to do is draw those esters there on the left. So that will kind of combine the understanding the esters groups with the naming, because you'll have to know how these are structured. So if you could draw those 4, that'd be excellent. And there's just another note as well: the lots and lots of organic compounds dissolve very readily in esters. So not only are they used as flavorings and perfumes, additives to perfumes and things, they're also widely used as solvents. So lots of things dissolve in them. They're very useful for that. So if you pause it here, give a go drawing those, and then we'll go through them. Okay, so here we've got the answers. Ethyl methanoate was the first one. And we've got it structured like this. So we've got the ethyl bit here and then the methanoate. 3-methyl butyl ethanoate. So the butyl bit is 1, 2, 3, 4. and it's 3-methyl, so 1, 2, 3. So 3-methyl-butyl is all this, and then the ethanoate bit. Then we've got ethyl 2-methyl-butanoate. So the ethyl bit is over here, yeah, meth, eth, so ethyl, and then the butanoate, 1, 2, 3, 4, 4 carbons long, and then it's got this 2-methyl group here. So ethyl 2-methyl-butanoate for all of that. The last one's probably the trickiest. Phenyl-methyl. Okay, so phenyl-methyl, and then ethanoate. Okay, so here's the ethanoate bit. So obviously this is a methyl group, so meth, eth, so ethanoate, and this is the phenyl-methyl part. Okay, so just the last thing then to look at is this reaction scheme here. This is what you're going to be doing in lesson, okay? And you're going to be reacting 2-hydroxybenzoic acid with ethanoic anhydride, and you're going to be forming basically an ester bond. So you're going to be forming, it's an esterification reaction, and between the ethanoic anhydride, and it's going to react over here to form this compound here. So just a little heads up there. That's what you're going to be doing to the synthesis of aspirin, essentially, with this molecule and ethanoic anhydride. All right, so hopefully all these questions are answerable now. So if you want to just pause here, jot them down, and we'll go through them. Okay, so can you give the reagents and conditions for forming an ester from an alcohol phenol? What about going backwards? So esterification of an alcohol requires an acid catalyst such as concentrated sulfuric acid under reflux. We use excess alcohol to shift the position of equilibrium to the right to have a higher yield of our ester, and obviously as well we need to use a carboxylic acid there. Ester hydrolysis requires an acid catalyst and excess water. So if we want to go backwards, then we need an acid catalyst and excess water. Esterification of a phenol requires an acyl chloride or an ethanoic anhydride and the absence of water. What properties do all esters share? Well, they will have strong fruity smells and are good organic solvents. And how are esters named? And make sure you're confident with naming some of those. So obviously the first part comes from the alcohol or phenol and it ends in -yl. And the second part comes from the carboxylic acid or acyl chloride or ethanoic anhydride, and it ends in -08. Okay, so hopefully that was clear. Good luck in the experiment and everything, and I'll see you next time.